Hello and welcome to this lesson on percentages. In this lesson we will ask the question, what are percentages, and look at how to calculate them. We will then look at one of the most common mistakes made in percentages questions before we look at what I call factors, which is a quick way to do percentages increase and decrease. The video will finish by looking at compound growth and compound decay. If you want to navigate around the video, as always, the links are in the video description. So what are percentages? Well, percentages are just a way for us to express one amount with respect to another amount. Examples that we use every day would be the mark that you get in your GCSE exam. You take the mark, you divide it by the total number of marks for the exam, and you multiply that by 100. That then gives you your mark as a percentage of the whole. A percentage is actually just a fraction where the denominator is 100. If you rearrange the three symbols that make up the percentage sign, the dash and the two rings, that is the number 100. We as humans have chosen this number 100, and it's arbitrary. We could have chosen the denominator to be 10 and we would talk about per deciges, or we could have picked it to be 1,000 and we would have called it per millages, but we've picked 100. This is because it gives us enough flexibility, we have lots of numbers to work with, without it being overbearing or cumbersome, like having a fraction out of 1,000. Okay, so let's quickly go over how we calculate percentages. Let's start off by talking about if we wanted 63% of 150. In order to conduct this calculation, we turn the 63% into a fraction, which is 63 over 100. We then times this by 150 and we get the answer as 94.5. Expressing the percentage 63% as 63 over 100 just shows what fraction of the total we are looking for. If the percentage had been 50, this would be 50 over 100, which would simplify to a half. If it had been 75, it would have been 75 over 100, which would have simplified to 3/4. And if we'd been looking for 100% of the total, it would be 100 over 100, which is just 1 when simplified. The other simple calculation that we would have to conduct is to work out what percentage a certain amount is compared to another amount. Let's take, for example, a test out of 200 marks where you get 180. In order to convert this 180 out of 200 into a percentage, we first turn it into a fraction of 180 over 200. This is the fraction of the marks that you got right. When we put this into our calculators, we get a decimal, and because the denominator is bigger than the numerator, this decimal is between 0 and 1. We then times this by 100 and we get our percentage. In this case, 180 divided by 200 is 0.9, and 0.9 times 100 is 90%. The fraction 180 over 200 could also have just been cancelled down by dividing top and bottom by 2 to get 90 over 100. This is a fraction and the denominator is 100, so the numerator is the percentage, 90%. Now I want to talk about one of the most common mistakes that students make in their GCSE exam when working with percentages. This could be roughly termed forgetting what your percentage is referring to. Let me explain with an example. Say you got given the following problem. There's a £60 coat in a shop, and the shop is having a 20% off sale. What is the price of the coat in the sale? Well, in order to complete this problem, we would work out what 20% is of 60, and 20 over 100 times 60 is £12. We then take this £12 away from £60 to get £48, the price of the coat in the sale. So far, easy enough. But what if the question was framed like this? There is a coat that was £60, but in the sale it costs £48. What percentage decrease is the coat in the sale? Again, this would start off quite easy. We would take 48 away from 60 to get our £12 reduction. This is the absolute reduction in cost. And the mistake that many people make is to divide this by the 48, while it should be divided by the 60. This is because when we say the words, what is the percentage reduction, we are referring to the original cost of the item. £60 is the original cost of the item before the sale, and therefore any percentage reduction will be with respect to that amount. To divide it by the 48 is wrong and will confuse you and make you lose marks. So remember what the percentage is referring to. Now let's talk about using factors in percentage increase and percentage decrease questions. In the RedTick one-pager, which I have here, we have written percentage increases and decreases as factors. For instance, if we have a 20% increase, it is better to just multiply by 1.2. To have a 5% increase, we multiply by 1.05, and to have a 12% increase, we multiply by 1.12. This also works with decreases, as a 30% decrease, you're better off multiplying the original value by 0.7. A 5% decrease, you're better off multiplying the original value by 0.95. And a 1.3% decrease, you're better off multiplying the original value by 0.987. This is a much quicker way than working out the percentage increase or decrease and then adding it on or subtracting. And here is why this works. Say we wanted to conduct a 50% increase of some value. Let's call it x. Using the slow method, we would work out 50% of x, which is 50 over 100, times x, which is 0.5x. We would then add that to the original value, which is x, and we would get an answer of 1.5x. This shows that we could have just multiplied the original value x by 1.5 to get our answer. Let's look at an example. Say we wanted to increase 300 by 50%. First of all, we might work out 50% of 300, which is 50 over 100, times 300, which is 150. We would then add this on to the original amount of 300 and get an answer of 450. But it would have been quicker to just use the factor of 1.5 times 300 by 1.5 and get our answer of 450. This also works with percentage decrease. Say we wanted to conduct a 25% decrease of a value. Again, let's call it x. The first step in the slow method would be to work out 25% of x, which is 25 over 100, times x, which is 0.25x. We would then take this away from x, and you can see on the board how we can factorize out x to get x upon 1 minus 0.25, leaving us with the answer of 0.75x. Let's look at another example. If we wanted to decrease 120 by 25%, we would work out 25% of 120. This would be using the slow method. 25 over 100 times 120 is 30. We would then take this away from the original value, 120, to get our answer of 90. It would have been quicker, however, just to multiply the 120 by 0.75 to get 90, and that would have taken us straight to the answer in one step. To work out what the factor is that you need to multiply by, either if it is a percentage increase, you divide the percentage by 100 and add it to 1. So 30% increase would be 30 over 100, which is 0.3, added to 1 to give us 1.3. But if we wanted a percentage decrease, we take the percentage, divide it by 100 and take it away from 1. So a 20% decrease would be 20 over 100, which is 0.2, taken away from 1, which is 0.8. Using these factors for percentage increase and decrease will make your work a lot quicker. It will also help you to understand the formulas for compound growth and compound decay, which is what we're about to go over. Okay, so now we're going to talk about the formulas for compound growth and compound decay. Compound growth, also sometimes called compound interest, is what happens when you put an amount of money into a bank account and it gains interest year on year. So you put £100 into a bank account and it made 5% every year. In the first year you would make 5% on £100, which is £5, and it would be added to the £100. So at the end of the first year you would have £105. But in the second year, The 5% would be taken as 5% of £105, not the original £100. So the percentage that you get in year 2 is going to be bigger than the percentage that you got in year 1. In year 2, this might seem like a really small difference, but over time, this amount of money grows exponentially. Compound decay is similar, but works in the other direction. Think of a car. A car depreciates in value. So a car may be worth £5,000, and it might lose 10% in value every year. The first year it will lose 10% of £5,000, which is £500, and it will be reduced to £4,500. But the second year it will only lose £450 because it is now 10% of £4,500. So the amount of money it loses every year gets smaller. Okay, so what about the formulas for these? Let's start off with the formula for compound growth or compound interest. This looks like a complicated formula, so let's go through what all the different letters mean. The formula is Pn equals P0 times, open bracket, 1 plus R over 100, close bracket, to the power of n. The subscripts on these numbers are not meaningless. The 0 on the P0 here means that this is the amount of money after 0 years, i.e. this is the initial amount. The n on this P tells us that this is the amount of money after n years. So this is sort of our answer or our final amount. The R here, this is the interest. So if the interest was 5%, R would be 5. If it was 3%, R would be 3. And this n is what we call the number of periods. Now, this is probably going to just be the number of years. If it's interest, interest is usually defined in numbers of years. But whatever the interest is defined in, interest over the course of a month or a year, this will be the period, and n is the number of periods. I'm now going to take this formula and put it down in the bottom right hand corner, and I'm going to show you how this formula is derived. This is important because it will allow you to use it much more flexibly, and also will help you simply remember it because you understand why it is the way that it is. Let's go through the following example. Let's say you have £1,000 and you put it into a bank account. Now, this magical bank account has 10% interest. No bank account ever has this amount of interest, but for this example, let's say it does. And let's say you keep your £1,000 in this bank account for 3 years. The question might ask, how much will the £1,000 be worth at the end of the 3 years? What I'm going to do is show you the slow method to do it. Then I'm going to bring in the factors that I talked about in the last part of the lesson. And then I'm finally going to show you why all this means that there's a formula for compound interest. Let's start off with the slow method. In the slow method, we would take 10% of £1,000, which is 10 over 100, times 1,000, which equals 100. This is how much money the account gets over the course of the first year. We would then take that 100 and add it to the 1,000 to give us £1,100 at the end of our first year. In year 2, we would then work out what 10% of that is, with 10 over 100 times 1,100, giving us £110 of money gained in the second year, and we would add that to the money at the start of that year, which is 1,100 plus 110, which gives us £1,210. That's how much money we have after 2 years. In our third year, we again would work out 10% of the amount of money at the start of the year, which is 1,210. 10% of that is £121. We would then take that 121 and add it to the 1,210 from the start of that year to give us £1,331. This being our answer. Okay, so let's now use factors. This whole step here could have been done by taking £1,000 and timesing it by 1.1. That's a 10% increase, giving us the 1,100 from the first year. Nice and quick. This second year could have been done a similar way, with 1,100 being multiplied by 1.1, giving us 1,210. Again, nice and quick. And the third year would have been done by taking 1,210, timesing it by 1.1, and getting 1,331. Those are our 3 steps. But what we've actually done here is take our original amount, which we call P0, we've times it by 1.1 once to get an answer. We've then taken that and times it by 1.1 again to give us an answer, and then we've multiplied that by 1.1 a third time. So what we've actually done here is take 1,000 and multiply it by 1.1 3 times. This is just 1,000 times 1.1 to the power of 3. This 1,000 here is P0. This n here, or this 3, sorry, is n. And this 1.1 is 1 plus 10 over 100. 10 over 100 is 0.1. And the 10 is r. We can therefore clearly see that this is P0 times 1 plus r over 100 to the power of n, giving us the answer, the final amount, of Pn. And this completes our formula for compound growth. Now we're going to go over the formula for compound decay. The formula for compound decay is very similar to that for compound growth. In fact, it's exactly the same apart from one change. Instead of having 1 plus r over 100 in our bracket, we have 1 minus r over 100. All the letters still mean the same thing, so I don't feel any need to go over that now. I'm going to put this in the corner while again we go through an example which shows why this is the formula for compound decay. Okay, in this example we have something that is worth £240 and it's going to depreciate in value by 25% every year. And the question would be, what is the worth of this object after 3 years? First, let's go through the slow method and talk about how we would do this problem in that manner. In the first year we would work out what is 25% of 240, which is 25 over 100 times 240, which is £60. We would then take this away from 240, giving us £180. That is how much this object is worth after 1 year. In the second year, we would again work out 25% of its new worth, which is 180, and this would give us £45. We would then take this away from 180 to give us £135, how much the object is worth after 2 years. And in our third year, we would work out 25% of 135, which is, calculator, 33.75. We would then take this away from 135 to give us a final answer of £101.25p. Okay, now let's look at how we could quicken up that process by using the factors. So in this first year, instead of multiplying it by 25 over 100 and taking that away from the original amount, we could just times the original amount by 75 over 100. This would give us our 180. So that's the working for the first year. In the second year we would take that 180 and we would multiply it by, let's multiply it by 0.75, it's the same as 75 over 100, and that would give us our 135. And in the third year we would take our 135 and times it by 0.75, giving us our answer of 101.25. There we go, 3 quick steps, very similar to what happened with the compound growth. But look again, we have our original amount, our P0 of £240, and in the first year we've multiplied it once by 0.75. In the second year we've multiplied that answer by 0.75, and in the third year we've multiplied that answer by 0.75. So in fact we've just multiplied the original value by 0.75 3 times. So this is 240 times 0.75 times 0.75 times 0.75, which is just 240 times 0.75 to the power of 3. Now this 0.75 is just 1 minus 0.25, which is 1 minus 25 over 100. The 3 is the number of periods, number of years, that's n, and this 240 is the initial amount, which is p0. So here we have Pn, our answer, equals P0 times 1 minus R over 100, all to the power of 3, which is the formula for compound decay.